there. And then I put my little cube in it. And I put all these arrows, stress vectors, on this place. Here. Exactly the opposite on this side. There's one there, let's make it a little smaller. Exactly opposite. And then there are these stresses here. So these are normal stresses and these are shear stresses. You could also see this as one vector pushing in this direction, one vector pushing in that direction, keeping the cube in equilibrium. Okay? These components balance each other, and if these components balance each other, there is still equilibrium. I hope you can believe this. And next year, in the advanced structural geology course, we will take a lot more detail on your construction. Okay. So now, I ask, here's my plane. What is this vector P? That's what I call it. On that plane, which is in such a way that they're in equilibrium with all these stresses. I can take away that half, and these stresses will not notice. So, to do this in an easy way, I'm going to make some very smart little definitions. So, I'm going to do it again. And I define my plane like this. And you could imagine to get really Newton for a square meter, that this is a kind of a little wedge. There is a third dimension. Is the length 1. I define this plane in such a way that it has an area which equals 1. I can do that. Okay. Define the normal to the plane as my vector L. This is my plane normal. So L has two components, L1 and L2. Still no problem. The area of this side of my little triangle is now equal to L1, because this has the area 1. The area of this one, just the same argumentation. So remember, this is how I define it. Area is 1, not the length, area. Okay. So, now let's just make another copy of this little diagram here. X1, X2. Here's my plane. And now on this plane, I have sigma 1, 1. And sigma 1, 2. These are the stresses which I take from that block. Okay, so I made a mistake. I still have to define what sigma 1, 1 and sigma 1, 2 is. I haven't done that yet. The way these are defined, this is the stress which is normal, it acts in the one direction, on the face which is normal to the one axis. So this is defined as sigma 1, 2. And this is defined as sigma 2, 1. This is sigma 2, 2. Okay. So in this phase I have sigma 2, 2. And exactly in this direction, sigma 1, which equals sigma 1, 2. And now, what I'm going to calculate is the value or the vector of the horizontal component, the one component of my vector P. Okay? So what I calculate now is P1, which is the horizontal. And for that, I need to use the formula for equilibrium. The forces in this direction have to be the same as the forces in this direction. Okay, what are those forces? Well, remember, force is pressure times area. So the force to the left, P1 times 1, remember the area is 1? That is the force to the left, equals sigma 1, 1 times the area, which is L1, plus sigma 1, 2, or 2, 1, I don't care, times L2. This is the horizontal component of my P vector on the plane. Now I'm going to go a little faster, and I'm going to calculate for you the two components of my stress vector. And I think that you will believe me if I say that V2 times 1 is sigma 1, 2, L1 plus sigma 2, 2, L2. Now I only take these components and then multiply them by the area. If I have derived P1 and P2, then I know the vector. So now, this is the little logic which was derived by Cauchy a long, long time ago, is that I can calculate the components of this P vector, the stress vector, inside a solid, in any given plane, by having the orientation of the plane, which is given by the L vectors, and these stresses which are outside the box, keeping it in equilibrium. And the big trick here is that to get the equilibrium of this little triangle, you have to go back to forces, because forces are the things which are in equilibrium, it's not the stresses. So force times the area on one side has to be in equilibrium with force times the area on the other side. And on this side of the little triangle, there are shear stresses which want to push it, and there are normal stresses. And all those things together have to be in equilibrium.
Hasn't there been a minus before the sigma 1, 2? Because sigma 1, 2 is in the minus x direction as there is P2. So P2 is in the same direction as sigma 1, 2. It has to be P1 times 1 plus sigma 1, 2 times L1, and then minus sigma 2, 2. So if you put it in another direction, it has to be a minus before sigma 1, 2.
Here?
Yeah.
Okay.
And there it's plus here.
Thank you. So, in fact, this is very interesting to hear because you are studying mechanics.
I'm studying metallurgical engineering.
In geoscience, the definition of these stress vectors is such that you don't use the minus sign. Depends on whether you define compressive stresses as positive or tensile stresses as positive. So the question that you brought up is very interesting, and this is one of the things that when you talk about stress vectors and tensors in the bar, then you can get a lot of confusion between students because geoscientists define it in a different way from metallurgists. Okay, now we should switch on the beamer. So although, let me just add one more thing. There is still one more way that you can tweak this literature. You can now go back to the first definition that we used and define the little cube. To be in equilibrium is stresses that are exactly normal to the face. This is not the most general case, it is a special case, but of course you can think about it. Then the calculations become a little bit simpler, and I will go through the derivation next year in the lectures for you. But what you can do now is you can again define this plane. And the plane normal. And you can define this angle, theta, between the x1 axis and the normal of the plane. And then you can go through the whole derivation again, and you can try, this is my P vector, which I should be yellow. You can now calculate the normal component and the shear component of this P vector. Once you have the P vector, of course you can calculate this normal shear component. And if you do that, I don't have time in this course to go through the derivation, but it's not very difficult. Then we have here the normal component shear component of this P vector. And for those, now of course these stresses on the side can be defined like sigma 1 and sigma 2, because they are now just normal in that phase. These are the principal stresses. And then you get this equation equals sigma 1 plus sigma 2 divided by 2 plus sigma 1 minus sigma 2 divided by 2 times the cosinus of 2 theta and the P S. This is now the shear component of the vector on that plane is sigma 1 minus sigma 2 divided by 2 times sinus of 2 theta. And this is a very interesting way to express the normal and the shear stresses on this plane. Because maybe you remember that in the quantitative geology course last year, we made a plot of the sinus of an angle against the cosine of the angle. If you plot the sinus of an angle against